In this video, I'm going to demonstrate how to use Truss Me to design the structure of a moon lander. Using the button for adding joints, we first insert two joints with the purpose of creating a protective cage around the payload. Using the button for adding bars, we then insert the corresponding structural members between joints. We must make sure that the payload is connected to the protective cage by adding all necessary bars. To see how the structure behaves up to this point, we hit the play button and start the simulation. As you can see, the landing gear is not properly attached to the protective cage, so we add two more bars to fix this problem. We now hit play again to repeat the simulation. As you can see, the two bars we just added fail. In this case, they fail due to a compressive instability called buckling. Let's take a look at this again. There are two ways of addressing buckling problems on bars. One way is to make the bars shorter. We can do that by redesigning the geometry of the structure. The other approach involves increasing the moment of inertia of the bars. In practical terms, this means making the bars wider. To do so, let's push the Make Wider button on Truss Me and then touch the bars we wish to make wider. As you can see, the overall weight of the structure increases accordingly. This is a penalty we pay when increasing the cross-sectional area of our structure members. If we run the simulation again, we can see that now the structure fails at a different point. This is a very important lesson of structural mechanics. When we fix a structure by making it stiffer somewhere, it most likely will fail somewhere else as loads redistribute. In our case, the structure now fails at the landing gear, again by buckling. So we are going to fix it the same way we did before. If we run the simulation one more time, we now see that failure is occurring on the top bar of the protective cage. As you can see, buckling is a problem again. We fix the problem by making that bar wider as well. We run the simulation again, hoping that this time everything works fine. The spacecraft landed safely without breaking any of its structural components, and the total mass of our first successful design is 53 kilograms. You can repeat the simulation as many times as you wish to better understand how the structure behaves. Colors during the simulation reflect the state of the bars. Blue means that the bar is under compression, that is, that the overall deformation of the structure is trying to make that bar shorter. Red means that the bar is under tension, that is, that the overall deformation of the structure is trying to make that bar longer. By looking at the structure, we realize that all bars at the top are under compression while all bars at the bottom are under tension. This can be understood intuitively by looking at the form of our structure. It's like if we built a compression arch at the top. So that bar over there is actually not helping much because it's making that arch a lot stiffer. The structure will be much more compliant if we allow it to deform without having that arch structure. So we could remove that bar and see what happens. So let's keep in mind that our weight of the structure at this point is roughly 53 kilograms. So let's see what we can get by optimizing a little bit our structure. Let's start by removing the top bar to give the overall structure more flexibility. Also, let's resize all bars to their original cross-section. By doing only these minor modifications, we can see that the overall weight of the structure was reduced by over 30%, with a new overall weight of 36 kilograms. We hit play and keep our fingers crossed, and the structure passed the test. Lots of deformation, sure, but it did pass the test. Basically, all the energy in the structure was dissipated on that lower bar under tension. So lots of plastic deformation on that bar, but the structure survived. Let's take a look at this again. The structure drops, hits the ground, the bars deform plastically and they dump the energy out. So let's keep looking how we can keep improving our structure. Those two nodes over there were originally to support the protective cage, but now we no longer have a bar there, so there is no sense in having those nodes up there. Having that in mind, let's move those nodes down a little bit, because now we don't need them there, so we can save even more weight by making those bars shorter. Now we are at 31 kilograms, so let's hit play and see how the structure deforms. And voila, we passed the test again. So let's try to make the structure even lighter. So we see all those parts at the bottom that are under tension. Let's try to make them narrower to see what happens. So now we hit the narrowing tool and touch those bars, hit play, and now the structure deforms a lot, and that bar over there yielded. So that bar failed by yielding. This is different than the failure we had before by compression. Now the bar is initially elastic and plastifies, and up to a point where the bar just gets cut in two. So let's put that bar again to its original size and run the simulation again. And we see that we passed the test. So we reduced the weight of our original structure by 50%. I hope you like this video, and this just shows a couple of capabilities of Truss Me and how you can use Truss Me to design and optimize structures.